Hello everyone, this is the solution video to assignment 11 of NPTEL 2023 Digital IHC Design course. So let's begin with question number 1. In this question, you can see that in figure 1, we have been given a clocked sequential circuit, right, with launch and capture flip-flops. We are given the sizes in terms of 1x, 2x for each of the gates. The gates are labeled I1 to I6, and we are asked to find out uh, what the frequency of the clock, right, which is synchronizing the launch and capture flip-flops. What frequency, what is the change in the max frequency that you can operate this circuit at, that is, you can operate the clock at if you had one stage of pipeline, right? So I will go over all the working that I have done uh, on the right hand side one by one, uh, right? So please feel free to pause the video at any point if you need to digest something, uh, right? So basically on the right hand side, you can see that there are various columns that are titled I1, I2, I3 and so forth, right? Each column, sorry, each column represents one gate in the circuit of figure 1. So I1 is this gate, it's labeled here as I1, it's labeled here as I2, right? So each column represents that gate, and above the column I have just drawn the the diagram with the 1x sizes of each gate, and in pink I have given the actual size that has been given in the circuit diagram for that gate. So let's start off with I1. So you can see that I1 has as a load through this fan out, right? It has as a load two gates, I3 and I4. So the first row is, okay, what is the load capacitance for this gate, right? So you can see that I3, right? So if you go to I3, which is over here, and see, okay, what will be the gate capacitance shown by I3? It will be 4 plus 1, right? Because the connection will be like that, right? A and B. So it will be 4 plus 1, right? And so that's what I have given here. For I3, it is 4 plus 1. But of course, I3 is a 2x gate. And so there is a multiplication by 2 into 4 plus 1, because this is the size of the 1x gate. The size of the 2x gate will be all the transistor sizes multiplied by 2. So that is I3. Similarly, what about I4? So in I4, it is going to look like this, right? The inputs. And so each input will see a transistor gate capacitance of 2 plus 2, right? And of course, I4 is also a 2x gate. And so that is 2 times 2 plus 2. So what are we, and remember, what are we trying to calculate here? We're trying to calculate that, uh, we're trying to calculate what gate capacitance is seen by the gate I1, by the logic gate I1 as its load. Yeah, that's what we're trying to calculate, right? We're trying to calculate what is the load capacitance in terms of transistor gate width seen by I1, right? So overall you will get 18. 18 is the load capacitance seen uh, by the logic gate I1 just from the connectivity of the circuit, right? And similarly, you can work it out for I2, I3, I4, I5 and I6, right? I5 and I6, if you notice, have zero load capacitance, right? That is because we have we mentioned that the load capacitance is zero uh, uh, for the pipelining stages, right? Uh, yeah, so this question that I am showing you here is not the latest version of the question, but if you go to the assignment configuration, you will see that capture flip-flops provide zero load capacitance to the gates I5 and I6 is mentioned. Oh, actually, it's over here, right? Provide zero load capacitance to any gate driving it, right? So yeah, that's why I5 and I6 are seen to have capacitance 0, right? So this is CL. We need to now find the CG, right, which is the gate capacitance of each gate, right, of this gate I1. And it's basically, you can see from here, right? So it will be 2 plus 2, which is equal to 4, and into 1 because it's a 1x gate. And CP, which is just the parasitic capacitance owed due to the drain diffusions of this gate on the output node, right? Right. So this will just be your CP, right? We find that it is 2 plus 2 plus 2, right? From this drain, and this drain. So that will just, and times 1x because it's a 1x gate. So that will be 6. Yeah, so once you have CL, CG, CP, you can get the logical effort, the electrical effort, and the uh, 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 and the parasitic effort, right? You also need to know what the reference inverter is, but the reference inverter the reference inverter is just going to be a 2-1 inverter for all these guys, right? Right, because these are all size for equal rise and fall delay, the reference inverter is going to be 2-1. It's just that for the 2x gate it will be 4-2, right? Yeah, so over here the reference inverter is just going to be PMOS of size, right, PMOS of size 4 and NMOS of size 2. Instead of 2-1, it will be 4-2 because the sinking current in this case, will be 2I, or the sinking or sourcing current depending on what the input logical input logic is, right? And so we need to ensure that the sinking or sourcing current in the reference inverter is also 2i, and so the reference inverter must be having a PMOS size of 4 and NMOS size of 2. So if you can see, in the reference inverter I have just done size into 3 for all the gates, right? So this is CP by C reference, right? So the denominator is the reference inverter size, and so that is just being multiplied by the uh, size of the particular gate, right? So let's start off by calculating the electrical effort. The electrical effort is just CL by CG, which is 18 by 4, right? 18 and 4, right? Similarly, we have your the logical effort, which is the CG by C reference inverter. So C reference inverter, because this is a 1x gate, right, is just 3. So it's 3 here, and CG is 4, right? So it's 4 by 3, 4 by 3, right? And then you have the parasitic effort, which is CP by C ref inverter, right? Which is 6 by 3. And GH plus P is the delay. So it's just 18 by 4 into 4 by 3 plus 6 by 3, which you will get to be equal to 8. And I have written 8 near I1, right? And like that, I have gone ahead and calculated CL, CG, CP, H, G, P, and finally D equal to GH plus P. for all the gates in this table, right? You can pause the video at this point to see if you are able to relate the table with the uh, relate the columns for I2 to I6 to what I just explained in the calculation of the entries in column I1, right? But the end result will be that you will get the delay values for each gate based on its load, based on the load cap that it's driving, right, and the size of the gate. So yeah, now I have basically annotated all those delays, beside the gate here. For example, I2 has size 8, I3 has size 22 by 6, I4 has, these are all the D values. I4 has delay 15 by 6, I5 has delay 2, I6 has delay 1, right? Uh, yeah, so the idea is now that we have to uh, get the maximum value that the that one stage of pipelining can improve the clock frequency at. So first let's get the unpipelined frequency, right? So the unpipelined frequency is just going to be 1 over the critical path delay. So from here, like by inspection, you can just see that the critical path, which is the path of longest delay, is going to be through this. That is I1, I3, and I5. Right? There are basically three paths, right? 1, 2, and 3. I'm sorry. Oh no, my mistake. There are basically three paths, which is I1, I3, I5, right? So that's 1. Then it is I1, I4, I6, that's 2, right? And then the third path is I2, I4, I6, and I2, I3, I5, right? So there are basically four paths, right? And if you look at the delay wise, the 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 max delay is going to come from either if you consider the path I1, I3, I5, or if you consider the path I2, I3, I5, right? Both of them have the same delay, so the max delay is going to be 8 plus 22 by 6 plus 2. And so the frequency that you can run this circuit, this unpipelined circuit, right, is going to be 1 over that, right? And yeah, and just by investigation, uh, you can see that, or rather, that the best place to put the pipelining flip-flop is at the 50% delay mark, right? The closest to that would be where I have drawn this pink, uh, you know, rectangle at, right? Right. So over here it will be like 8, and over here it will be something like 22 by 6 is roughly 4, so it will be 6, right? So 6 and 8. That's closest. That's closest. That's the best you can get towards 50% of delay on each side, and so that's where we will place the pipelining flip flops, right? And yeah, so because of that, now we can get that uh, by the frequency that which at which you can operate clock. Remember, now clock is also going to be coming to the pipelining flip flops, right? So the frequency at which you're going to operate this circuit, right? The frequency of clock at which you're going to operate this circuit is going to now be 1 over the max delay of this and the critical path delay of this, right? The max over the critical path delay of both the pipeline segments, and that is clearly 1 over 8, right? And so if you see what the value of k is from the question itself, k is equal to f is equal to k over t after pipelining, f is equal to 1 over t before pipelining, right? So k is just going to be uh, f pipelined by f unpipelined, right? This is just k by t divided by 1 by t, just k, right? So that's correct. So k, which is like the speed up factor, is now going to, you can get it from this calculation, right? It will come out to be 1.7083, right? And the question, I believe, has been configured to plus or minus 5, I believe, plus or minus 5 e 1.70, or rather I should just say that the range of the answer is basically plus or minus 5e3. Yeah so this is the range to which the answer has been configured, right? 5e minus 3, not 5e3. And yeah, this is the question. And now if you're allowed to add two stages of pipelining, what is the maximum value that k can take? So the maximum value of the speed up now will not change, because you can see that uh, it's not like you can't break these gates further in, right? So this 8 will always be the will always come out to be the max. Let's say even if you put some pipelining like that, right? It's now going to be the max of the three pipeline segments, and that max delay is just going to be 8, right? Just from a visual, inspection. And so the answer does not change, right? So for questions 3 to 9, one can see that we have configured, two gated inverters, right? So an inverter that has been gated with a clock bar, right, as a sequential circuit. Right? It's just that the this has clock bar. The sequential element 1 has clock bar and clock. Sequential element 2 has clock and clock bar, right? And because of this, and you can see that if you just look at sequential element 1, when clock equal to 0 and clock bar equal to 1, it is opaque, right? There is no D cannot influence QM. And when clock is equal to 1 and clock bar is equal to 0, it's basically an inverter, right? So this is like a an inverting latch, right? An inverting D latch, right? Yeah, so and you put two of them in series, you will get a D flip flop, right? So that's basically question 3 and 4, right? Uh, it's a negative edge triggered flip flop, because when clock is equal to 0 and clock bar is equal to 1, right? 0 1, you will see that the value of q is sorry, when clock bar is equal to 1, you will see that the value of q gets affected, right? uh, it will possibly get changed depending on what the q and qm states were just before this neg edge, right? So at this neg edge is only when the output changes, and so we name it based on the edge at which the output changes. It's a negative edge triggered flip flop. And if you just look at if you remove sequential element 2, right? So if you remove sequential element 2, right, the remaining circuit with input D and output QM is a so when clock is equal to 1 and clock bar is equal to 0, this is in the transparent case, right? The output D, the latch output is affected by the input, right? And so it's a, positive latch, right? And yeah, so those were questions 3 and 4. Questions 5 and 6, you can see that since it is a uh, uh, since the input latch is a positive latch, right? So it's basically a master slave flip flop. So the master is the sequential element 1 and the slave is sequential element 2. So since the master is a positive latch, and you can see that this is like I can just mark the phases opaque and transparent, right? This is the phases of clock, and yeah, you can see that D1 is completely in the opaque phase, so it will not even affect QM, so it won't even affect Q, right? But however, D2, D3, and D4 are completely are present in the transparent phase. and there is no and they are present until the point of the negate, right, without any change. So therefore they will reach qm, and also they will reach q, right. Something can reach qm but not reach q if it changes something like here, right, just before the uh, just before the transparent phase finishes, right, just before sampling finishes. And so because of that, you can see that the answers that are configured are basically D2, D3, D4 and D2, D3, D4, for which one of them reach QM and Q respectively. Right. So now in question 7, assuming that the transistors have terminal currents as per the unified current model, right? Uh, 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 Basically, the key takeaway from the unified current model is that there is no leakage. That is, I is equal to 0 for when VGS is less than VTH, right? So given a long enough clock period, the circuit is guaranteed to be functional, right? So no leakage, so is means not affected by clock period, and no matter what the strength of the and this is the drain current of the transistor, right? Basically, and no matter the strength of the input driver, the strength of the input driver doesn't matter anymore, right? Because we are giving a long enough clock period, the nodes will rise, right, and they will not leak because it's a long enough clock period, uh, right. So also right, so no matter what strength you had given for this whole circuit, right, the nodes will rise to the correct level, and in fact the input driver is not is only going to determine the strength of the gate rises, right. So yeah, it's not going to determine the functionality. And so, yeah, the answer for question 7 is A. In question 8, right, the circuit will stop working for some clock frequency less than some Fmin, right? That is some clock period greater than some 1 by Fmin, right? That's true because what will happen is you can just imagine sequential element 1 to be like this, right? An invert, a gated inverter. You can imagine it like that. As soon as this goes up, right, the diffusion capacitance over here, the capacitance over here, which is a combination of the gate capacitance of the sequential element 2 and the diffusion capacitance of basically these switching kind of in between switching NMOS and PMOS devices, right? This gate capacitance, this capacitance will start leaking, right? If see, because we have given this statement of IDS is not equal to 0 when VGS is less than VTH, right? So it will start leaking into ground basically, right? And because of that, given a long enough time, this will like lose the charge that is stored on it, and therefore the information stored on it, right? And it will stop working. So the answer for question 8 is true, right? uh, Noise in the input node can disturb the internal state when clock is equal to 0. That's not true, right? So when clock is equal to 0, uh, it is basically the input, right, uh, right, the internal state is basically qm, right. So it's this is what happens when clock is equal to 0, right. You have basically qm here. This node is the internal node in the master slave flip flop, right? And this is Q, and this is D. So if it doesn't matter if there is noise over here because this is open, right? And of course, when clock is equal to 0, this is like it's a master slave flip flop, right? So that's closed. That switch is closed, and this switch is open. So yeah, noise at this node does not have any effect on this node, right? So so the question is phrased as can disturb, and so therefore the answer is false, right? So for question 10, race condition due to clock overlap on the sampling edge, right, cannot be overcome by imposing a hold time constraint. No, it can be overcome by imposing a hold time constraint. You can refer to the lecture on race, right, in a master slave for the answers to this question, right. Cannot be overcome by imposing a setup time constraint. That is true, but yeah, there is no point in imposing a setup time constraint, right, because of the uh, right. So it's only going to be helped by imposing a hold time constraint, and so the answers are B and C, right. So in figure 4 we have the common figure for questions 11 to 13, right. This is basically a uh, uh, like a latch, right, and and the elements that make up this latch are given in different colors, which is TG like TG1, like I1, I2, and I3, right? And yeah, I leave it to the reader to try and understand how this latch will work when clock is equal to 0 and when clock is equal to 1, right? So it's very straightforward. It's just that this will the input connection will be cut, right, when clock is equal to 0, and this connection will become like transparent, right, when clock is equal to 0, and in the opposite, in the other polarity of clock is equal to 1, clock bar is equal to 0, the this is basically like transparent, and these two are cut. So you can look at the figure to find out what the consequences are if for those particular breaking of the feedback or breaking of the input, how the circuit is expected to work, right? But the delays of these elements are given over here, right? And based on these, we have to assume that there is a instantaneous non-overlapping clock edge, right? So if this is clock, then uh, this is clock bar, right? It's instantaneous, we assume, and we go ahead and try to answer questions 11 to 13. Right, so question 11, what is the type of sequential element? It is a positive latch, right? Given what I have just said about what will break and what will open for the different phases of clock, I think it's fairly straightforward to understand why it's a positive latch. So I will leave this to the reader to understand. What is the TTQ of the sequential element? Right? So the TTQ is basically the amount of time for when the latch becomes transparent for the data to go from D to Q, right? So when this is transparent and this is opaque, right? Which is the phase of clock equal to 1, clock bar equal to 0. The amount of time it takes for a change in D to appear as a change in Q. So you can just see that this is going to be Tg1 plus I1 plus I3, right? Just from the elements that are attached, Tg1, and then we follow this to I1, right? And then we just follow that to I3, and then we reach Q, right? And yeah, so that will be those will be the delays involved, right, when we are in the for this positive latch, right? So Tg1 plus I1 plus I3 is 4 nano. Similarly, the setup time is going to be Tg1 plus I1 plus I2, right, which is just fairly straightforward. The amount of time you need to wait before you can close the amount of time before the sampling edge closes, uh, uh, that the input D must become stable, right? It's just going to be the amount of time it takes for this portion of the circuit to stabilize, right? What I've drawn here, right? Which is just Tg1 plus I1 plus I2. This comes out to be 5 nano, right? Right? And driver strength is not an issue. Yes, because of the brake feedback design, the driver strength is not an issue. T clock to Q, it's just going to be the TDQ. right? And what is the T hold? So there is no hold delay because it opaques instantaneously, right? Yeah, because the clock, because the transmission gate basically opaques instantaneously, right? There is no effective hold time uh, requirement for this gate. So the any driver to this gate can immediately start glitching after the clock, edge, after the sampling clock edge. So yeah, the answer is 0 for question 16. And so those were the uh, answers to assignment 11 of NPTEL 2023 Digital IC Design. Thank you.